Welcome back, students. We have been talking about electromagnetic induction. We have been saying that if a magnetic field changes, then if you have a loop of conductors, then current will flow through that loop. And that is because an EMF will be induced because of the change in the magnetic flux. And that EMF will send a current through the loop if it is a closed loop. So that's what we have been discussing. We are going to take that a little further, and then we'll talk about what is called as eddy currents today. Okay. Even before going there, I just want to imagine this scenario. Suppose that you have a magnetic field like this. So this is B, which is inside. Okay. And let's say that I have a loop. Okay. It can be a square loop or a circular loop or any type of loop, doesn't matter. Let's suppose that I have a loop. Or it can even be a square loop or a rectangular loop. So this is loop 1 and this is loop 2. And if you vary this field, it's not a constant field now. It may have some value at one point in time, and if you vary this field, then what will happen is that the flux through this loop is changing. So there will be an EMF induced in this loop A. I'll call this as loop A. Okay. And this EMF will circulate a current in such a way that will oppose the change in the magnetic field. So will be the case with this loop. I will call this as loop B, which is a rectangular loop. Because this flux is changing, then this will produce an EMF, and then that EMF will make a current flow through this loop. What if I have another loop here? Same thing will happen. And what if I have another loop here? Same thing will happen. The amounts of current could be different, but the phenomenon of electromagnetic induction will be happening in all the loops. Whatever be the shape or size of the loop, it will be happening here. Like that. You can see this. What if I bring a plate instead of these different loops? Let's suppose that I have a plate. I have a plate here. Now I vary the flux. Then you can see that this plate will have an infinite number of loops inside. So each loop in the plate, maybe like this, like this, like this, like this, all these loops will be circulating currents because the flux through that is changing, and those because of change in the flux, an EMF will be induced at every level and current will be circulating the plate. So if I have a plate, then I will have currents inside the plate circulating inside. So clearly that current, those currents basically will have an I squared R loss and heat up this plate. So if I keep a plate and then if I vary the magnetic field, then what happens is that this plate will get heated up basically. There will be an I squared R loss. because there is current flowing through that. And this current is what we call as eddy currents, because they look like water eddies. The circulating currents, they look like water eddies. So that is why you call this as eddy currents. This is a major phenomenon. Okay? This is present in almost all instruments which will require a core. For example, if I have a transformer or even a motor, okay, you will have a core around which you will wind the wires, and that core would be a ferromagnetic core, because you want to increase the flux that is going through the core, because the more flux, the more change will happen. Rate of change of the flux will happen as you run the motor. Then there is more output, clearly, and more greater EMF will be generated. Whether it is a generator or a motor or even a transformer, and all these instruments will have a core. And because you have this core, there will be eddy currents in the core, because this phenomenon that I talked about, that will be happening in the core. For example, I have a cuboidal core. And suppose I have a core like this. And suppose I have windings going around that core. And let us also suppose that this is kept in a magnetic field and flux is going through this. Magnetic flux is going through this and then coming out of it. And I have windings around it for some reason. I might have windings. This is the wire. Okay. So imagine what is going to happen, because the flux is changing, then this core will act like an infinite number of these sheets. Notice? So there will be eddy current here in this, and then inside, and I'll have multiple sheets, an infinite number of sheets. So at every distance, I'll have eddies getting created. So these will be producing the I squared R losses, because the currents are flowing inside the core. And EMF will be generated here. That's all fine. And the blue is the winding, and this is the EMF that you are going to make use of. This is the voltage which is generated in this is what you will make use of. But what is happening inside the core, you can't make use of. It's all happening inside it. And the current will be flowing inside the core, heating the core up. This core will be heated, because an EMF will be induced not only in the windings, but will also be in the core. So the core will get heated up. And clearly that loss of energy, that heat energy, must be given by U. Either when you mechanically rotate the core, the winding, or when you, in the case of a motor, you will supply electricity for that to rotate. So you are going to give the energy. So you will be losing energy. When the energy that you give would be lost here, either as heat, something. It won't be available for. The conversion will not take place. In the case of a generator, you may give mechanical energy and get electrical energy, but a part of your mechanical energy will be lost here. As the core produces eddy currents and heat, so the energy for that has to come from somewhere, and who is giving it? You, by rotating the rotor of the generator. This is what you are providing mechanical energy. So the energy you give would be, a part of it would be lost here. And what you get out, the conversion of mechanical energy into electrical energy would be less than what you give, because part of what you have given is lost here. That is in the case of a generator. But in the case of a motor, you give electrical energy and then you want mechanical energy. But then also this thing will be happening. Eddy current will be happening, the I squared R loss will be happening inside the core. So you will have to give more electrical energy, and that part of the energy would be lost here as heat, and whatever is remaining you would get as mechanical energy. So eddy currents would be a major phenomenon in these things. So how do you control it? You can't reduce it completely. How do you control it? Well, it's very, if you think about it, you all will also know how to control it. Okay? So let me take this. So this is my plate, and here is where I'm going to have my eddy current. Let's say eddy current. So if the circuit is complete, then eddy current will flow in this. But what if I break it here? What if I make it, what if I have an insulation here? Then I am breaking the loop. If I break the loop, then clearly, and so much current will not flow. Likewise, I am going to break it at a level. So in that case, if the less current will also not flow like that. Maybe the current in this will be flowing, but that's going to be very small amount. So if we keep having these laminations, if we laminate this core, instead of making it as a single solid material, I'm going to keep as plates which are joined by this insulating material. So it's called as lamination. So you have a core, then you make the core out of small pieces joined together by insulation. So in that case, you won't have any big circles. Maybe you will have a very small circle here, a small amount of current, but you would have reduced a lot of current flowing through this core and creating a lot of heat. So the laminated core, this is called as lamination. So the laminated core is the way you reduce eddy currents. So the loss will be very small if you use a laminated core. If we just keep it as one solid material, then all kinds of currents will be flowing. I told you. So different kinds of currents will be flowing. But if I laminate it here like that, then only a small circle of current will be flowing. All these circles will not complete because there will be a gap where there is an insulation. If we have insulation here, this insulation, so there is a break in the circle. So the circuit will not be completed for these big currents. So only at a very small level, eddy currents will be happening. So, but this way I can reduce the effect of eddy currents. I can reduce the effect of eddy currents by using laminated cores. Okay. Or there is a beautiful example given in your book. It's like this. the example given in your book for eddy currents. See, it has a magnet, North Pole, South Pole, and then you have a plate, a metallic plate, which is hanging from the ceiling. So you have magnets like this, then there is a plate hanging from the ceiling. So what you do is, you take this plate away, in this case this side, away, and then if you leave it, then the plate is going to oscillate, right? It's going to come into the magnetic field and then it will go out of the magnetic field. Then it's like a pendulum, it's going to do this oscillation. Okay. Let us see what will happen when it does this. Okay. So this is going, this plate is going to go into the magnetic field. This is north, this is south. So field lines will start from north and then go end in south. So in the south they will go into it. So that's why you got crosses here. So now this is going to come in. You see, as it comes in, notice that the flux through this conductor, this plate, is increasing. As it enters, as it is crossing and then getting into this, the flux through this is increasing. So an EMF will be induced. The flux through this is changing. There is no flux now. As it comes in, flux through this will be changing. As it changes, an EMF will be induced. And since an EMF is going to be induced, and since this is a plate, a continuous thing, not just a loop, since it's a plate, then it is going to circulate current. So there will be eddy currents produced in this plate. Which would be the direction of that current? Yeah, clearly the flux is increasing, so I have to reduce the flux. This current should reduce the flux. So which direction the flux is going? It is into this S, south of this magnet. Okay. So this flux must be reduced. If this flux must be reduced, it has to put flux in this direction. If this has to put flux in this direction, current in this must be like this. So current must be flowing in the counterclockwise direction in this plate. So the eddy currents, all eddy currents, you will get lots of eddy currents here. So they complete the cycle. So all the currents will be in the anti-clockwise direction. And now it has gone into the magnet. Suppose it is here. Suppose it is here. The center. Would there be any EMF induced? No. But even though this is moving, no EMF will be induced because the flux through this is not changing. It is the same flux through it, whether it is here or here or here, same flux. As long as it is inside the field, the flux through this is not changing. But what happens when it tries to come out? When it tries to come out, then flux through this changes. How does it change? It is actually decreasing. If it is decreasing, then this should put current in the direction such that it increases the flux. So which flux is decreasing? This flux is decreasing. Okay. Then I have to increase the flux. In that case, which way I should put the flux? This way. If I need to put the flux this way, then what should be the direction of the current? The current must be in this direction, which is the clockwise direction. So as this comes out, as this is here, as it is coming out, it is coming out too much, but I'm saying as it is leaving, I should draw it properly. Let's say as it is leaving, okay, it's leaving, then this would be in the clockwise direction. Current will be in the clockwise direction. All the eddy currents will be this direction. Okay, so this is the direction of current. So that is anti-clockwise, and this would be clockwise. As it enters, you will have clockwise current going, and as it leaves, you will have anti-clockwise currents going. Okay, but you can see this. You can see that this will be slowed down as it enters. Why? Because a force will be acting on it. The force that is acting on it would be opposing this. For example, let me take this bit. Okay, the current is like this, right? The current is, if you take this bit, the current is down. Current is down. Flux is this way. Okay. IL is down. IL cross B, then just notice the force will be in this direction. So as it tries to move, there will be a force which will oppose that motion. So this will slow down. The force will be acting in this direction as it enters. It will slow down. Likewise, as it tries to leave, then the force will try to bring it here. Okay, so you can see that, like you can do it yourself and you can find this thing. Anyway, so as it gets in, then it is slowing down. This is the idea they use in levitation. The trains, super fast trains. The super fast trains, they use this magnetic levitation as as the principle. So there is not much of friction involved. So it is very difficult to stop those trains. They are going very fast, and there is very little amount of friction. They are not touching the rails or something. So very little amount of friction. So without friction, how will you stop something which is moving? This is what they use. They use this principle to produce eddy currents in the brakes and slow down the train without friction. So eddy currents, when I talked about eddy currents, I gave you the negative points in the beginning, that it is using up a lot of heat and stuff, and it's using energy to produce heat, and it makes an instrument inefficient because the amount of the energy conversion that you want to happen in it doesn't happen as much as you want, because part of the energy you give goes in producing this heat in the core. So you need to go for lamination and stuff, and even there you will not completely eliminate it, but you will reduce it. You can keep it to a minimum. So the eddy currents will be there. These are the negative points that I talked about. So, and to reduce that ill effects of eddy currents, you are going for laminated core. This is what I said before I talked about this. But that was a negative point. But this is also a positive point. This can slow down. You can see that this is going to get slowed down. Because it can get slowed down, this idea can be used in super fast trains as brakes. So you don't require friction. So you can keep friction to minimum without touching the rails, without touching the floor. The trains can go slightly up and they can move. But if they are not, the friction is so less, then how do you stop the trains? I can use this method, eddy currents, to slow down the trains, because the train is moving and it's going to act like this plate. Now if I have powerful magnets, then they can slow down the train and bring the train to a stop. So this is what eddy currents is all about. And another thing that you can observe is this. Okay, so this is one full plate, right? As it enters, it's one full plate. So it will produce a lot of eddy currents. But what if I have these sections? Like I'm going to make this as a tooth. Okay, I'm going to cut this and then convert that into if I do this, instead of one full plate, if I cut this and make as these teeth and allow it to go, then not much eddy current will flow through this, and it won't be stopped as fiercely as this one is. Like if it is, the force acting on it would also be small because I cut it. I'm not allowing the path to complete. So not big currents will not flow. Only small currents here they might flow. Okay, this current they might flow. Again, current can flow here, current can flow here. But because I cut this into teeth, I'm not providing too much of a too big path for the current to flow. Not lot of current will flow through this. So this will not be slow down as much as this will slow down. This will really slow down, but this will slow down but not much. It will the force on it will be less than the force on this because currents in this will be small. So this is another way of reducing the eddy currents in instruments. So either you can go for laminated cores or you can have this T kind of setup. So this way you can reduce the eddy current. In both cases, you are not providing big paths for the current to flow. You don't give big circles, not too much flux changing, and having that loop to send a lot of current. So that way you reduce the losses, and you can also make this not slow down as much as that slows down. The next concept that we are going to talk about is inductance. There are two types in this inductance, and they are, one is mutual inductance and the other is self-inductance. First we'll talk about mutual inductance and then we'll talk about self-inductance. But before even we do that, let's define what is inductance. Okay? Let me take two coils. There is a coil here and let's suppose that I pass a current through this. Current I is flowing through this coil. So clearly, this is going to set up a magnetic field around it. Okay? Magnetic field around it. As it sets up the magnetic field, I'm going to bring another coil. Let's say like this is going to expand, right? So like that. I'll bring another coil. If I change the current in this coil, then clearly the magnetic field produced by this coil will also change. The strength of the magnetic field will change. And notice that the field lines go through the other coil too. So the flux through this coil will also change. And because the flux through this coil changes, then there is an EMF induced in it. Okay. So if you take just one coil, okay, like if you just take one loop, then the flux through that loop, phi B, is proportional to the current I in this. This current is the current which is flowing in this coil, and that produces a flux, and that is flowing through this coil too. And they have taken just one loop. So that one loop, that flux through that one loop is phi is equal to B into the area of that loop. So that flux is proportional to I. If I increase I, then that also will increase. If I decrease I, that also will decrease. So that is phi B, which is proportional to current in this. And if I have n such turns, closely wound turns, then I'll have this n phi B, and this also will be proportional to I. Because if phi B depends on I, then n phi depends on I too. So that is also proportional to this. So this n phi B I call as this one. This term I call as flux linkage. Because there is a total amount of flux that links the coils. So this is flux linkage. This is flux through one loop, phi B. N into phi by is the flux through the total coil. It's called the flux linkage if it has n number of turns. But both of them must be proportional to I. If we change I, phi will change. If phi changes, n phi will also change. So this also must be proportional to I. And clearly, the EMF induced in that coil E is equal to minus N into d phi B by dt. Okay? And clearly, that must also be proportional to di by dt, how much the flux changes. Phi depends on I, so d phi by dt depends on di by dt. That's natural. And if I introduce a constant of proportionality here, what I'm going to get? I'm going to get n, say d phi b by dt is equal to L into di by dt. So this constant of proportionality, L, is called inductance. This is what I call as inductance. Because this is a constant that talks about induced EMF. So it's a measure of that induction. So you call this as inductance. So phi is proportional to I, which means n phi b is proportional to I, flux linkage is proportional to I. So d phi dt must be proportional to di by dt, and if I introduce a constant of proportionality, then I call that constant as inductance. Okay. And what is the unit of this inductance? Well, that's easy. Okay. This is EMF induced. So L dA by dt is EMF finally, because L dA by dt is N d phi by dt, it's nothing but EMF. So that's in volt, 5 volts, 10 volts, 1 millivolt, whatever. So this EMF is going to be in volts. So if I take this L dI by dt is equal to, I'm going to ignore the negative symbol because I'm focusing on finding the unit for this. So I'm going to ignore the negative symbol. So I will say this is E. Okay. So I need to find L. L can be written as E to dt by di. So this is volt. This is volt, right? This is unit for this. I'm going to do unit for this now. Unit for L. This is volts, and this is change in time, which is second. And di is change in current, which is ampere. So this is a unit. And if I expand on this, what is volt? Volt is nothing but joule per coulomb. So joule per coulomb, and write this as joule, second. Coulomb, I can write as ampere second. So ampere second is ampere. So I modify this. Instead of volt, I have written joule per coulomb. This and this will cancel. So that will give me joule per ampere square. But I can still reduce it. What is joule? Joule is Newton meter. So I will say Newton meter per ampere square. Again, I can reduce Newton. Newton is written as kilogram meter per second square. So finally, the kilogram meter per second square into m by ampere square. So that's going to give me kilogram meter square by a square s square. So this is the unit for inductance. But you're not going to, in real life, you're not going to mention this. You're not going to give the unit of inductance as kilogram meter square by ampere square second square. You're not going to say that. Instead, you will say that this is Henry. The unit of inductance is Henry. This is to honor an American physicist, Joseph Henry. And he too discovered electromagnetic induction independently. When Michael Faraday discovered it in England, he discovered that in the US. They did that independently. So, to honor him, we are giving a name to this unit, and that is his name. So, Henry is kilogram meter square per ampere square second square. Hope this is clear to you. Next item that we are going to discuss is mutual inductance. We said that if I have a coil which has current I flowing through this is going to set up a magnetic field, and if I have another coil here, then this change in the magnetic flux will affect this coil and it will induce an EMF in this. And what if this coil is also carrying a current? Let's say this is I1 and this is I2. So there is this current flowing through this, and because of this current there will be a flux in this magnetic flux, and that flux will link this, and if this current changes, then the magnetic flux due to this current will change in this coil, and that coil will produce an EMF. So the change in the current in this coil will produce an EMF here, and the change in the current in this coil will produce an EMF here. So there is what is called as mutual inductance. So they induce EMF mutually. One induces EMF in the other, and the other induces an EMF in the first one. So this is mutual induction. And we can have a quantity for this that is called as mutual inductance. How much a coil influences the other coil. So that is mutual inductance. That is what we will do it now. So now we will take a simple case of two coaxial solenoids. Okay. So I have a solenoid like this, a big one, like that. And I have a small solenoid inside that. And both have the same axis. So they're called as coaxial coil. So one solenoid inside another solenoid with axis being the same. Okay. Let's say I will call this as a solenoid 1, and let's say like it has a radius 1. Okay, let's say like this as a radius 1. It's radius 1. And let me also say that current I1 is flowing through this. And I'll also say that there is N1 turns per unit length for this. And I can do the same thing for the other thing, the other solenoid. So this coil I'll call solenoid I call as S2, and this radius I'll call as R2, and current through this is I2, and N2 will be the number of turns per unit length for the bigger solenoid. Now, what do we know? Let me first talk about the first solenoid and what's going to happen to that. I'll talk about inductance of that. Okay. So what do we know? If I take this, what is the flux linkage in this? In the first coil, S1. S1 flux linkage. S1. If I talk about S1, the flux linkage is equal to N1, okay, N1 and phi, this phi due to the other thing, the other coil, the flux from the other coil, that would be phi. I call this as phi 1 for the time being, because even though I call this phi 1, this flux is given by the other coil, N1 phi 1 B. Okay, magnetic flux through this coil, but this flux should be given by that one, by S2. Okay, and we know that this N1 phi 1b flux through this is equal to, it's actually proportional to I2, and then because of constant of proportionality, and there must be an L, right, inductance. So in this case, I'm going to say it's going to be M12, because instead of L, I'm going to use M for mutual inductance, and 1, 2. That is mutual inductance of 1 due to 2. I want you to understand this. Mutual inductance of 1 due to 2, which means that I must be taking the current through S2. So that is I2. So this I2 will produce a current, will produce a flux, and that flux will link this coil. Because if you take S2, I just draw this. If I2 is flowing through this, then there will be a flux set up here. There will be a flux. I don't know the direction of it right now. Okay. So I2 is going like this. Okay, so then flux must be like this. So, but this flux is due to S2. But notice that part of that flux goes through S1, and this is what I mean by the flux linkage of S1. The flux from I2. Okay. Not its own flux. The flux is from I2. So this is what you get. Now I need to calculate phi 1b. What is the flux through this now? Well, the flux through this, to calculate the flux through this, then I need to find the magnetic field strength and multiply that by the area, then I will know the flux. Right? So we will do it now. Okay. So what would be the magnetic field strength due to I2? That's going to be B2 that is given by, from our previous discussions, this is mu naught N2 then I2. Mu naught Ni. Mu naught N2 is number of turns per unit length for S2, and I2 is the current flowing through S2. So mu naught N2 I2. So then phi 1b is equal to B2 into area of S1. So area of 1, right? So that would be B2 is mu naught N2 I2. A1 is pi, this is R1, pi R1 square. So pi R1 square. Okay? Now I am going to take this and substitute that here. So this is my equation 1, and say this is my equation 2. And if I substitute 2 in 1, then what I'm going to get now? So I'm going to get N1. What is N1 now? N1 is total number of turns in this coil. That is given by here N1 can be given by N1 into the length of this coil. Both of them have the same length, let's suppose, and this is the length. Okay, length L. So N1 into L will give me the number of turns in S1. So I'm going to substitute 2 in 1. Okay, so I'll get what I'm going to get for here. This would be N1 L, and that is equal to N1 L, and for phi 1b I'm going to put this mu naught N2 I2 by R1 square. So this must be equal to M12 to I2. Okay. So from this I can easily find M12. So M12 is equal to this I2 will cancel. So I will get N1 N2 mu naught L to pi R square. This is the mutual inductance of 1 due to the current flowing in 2. Okay. So now let me do the same thing for the S2. The mutual inductance of 2 with respect to the current flowing through S1. How do I do that? I need to take this same stuff, right? I need to take N2, so S2, I'll take S2 now. For S2, flux linkages, flux linkage is going to be N2 into this flux. What our flux is going to be? N2 into phi 2b. Okay. So this would be equal to the mutual inductance of 2 with respect to 1 multiplied by the current through 1. So what would I get here? What is phi 2b? Phi 2b, if you take all the, because it is inside, these are two coaxial solenoids, right? So we're talking about the big one and small one, and we're going to take the flux passing through the big one due to the small one. You see, all the flux that the small one produces will pass through the big one because it is inside that. Okay, so here it is going to be N2 is fine, and phi 2b will be the flux produced by this into this area only. That's the total flux for this also. You are not going to use it for this area. Okay, notice that the flux is limited here. We know that for long solenoids, the flux outside the solenoids will be 0. There is no flux outside this. So there is flux only inside the inner solenoid. So this is equal to N2 into what is phi 2b? So phi 2b is going to be, I'll write this here. What is phi 2b? Phi 2b is going to be B due to 1 and then area of 1 again. Exactly. Because you don't have, but in other areas, it's only here. There is no flux due to this outside. All the flux is inside only. So only this area I can take. It's a total flux. So B1 and A1. And what is B1? B1 is given by mu naught and then N1 into I1. That's a magnetic field due to this solenoid. And multiplied by that area will give you the entire flux. There is no flux outside. So into A1. Okay. That will be pi R1 square again. So this is going to be equal to mu naught N1 I1 and pi R1 square. I am going to substitute that here. So this will give me mu naught into N2 into mu naught N1 I1 pi R1 square, that is equal to M2 1 then I1. Then I can cancel this. I1 and I1 can cancel, then M21 can be written as, what is N2? Number of turns in the second coil, right? That is equal to N2, small n2 into L. Number of turns per unit length into L. So I'm going to have N2 L, then mu naught N1 pi R1 square. Okay. So if I rearrange, then I will get M21 is equal to N1 N2 then mu naught L into pi R1 square. Okay. So if I call this as 3 and if I call this as 4, you can see that 3 is equal to 4. So mutual inductance is same for both the coils. It has to be. Because if one affects the other in one way, and the other should affect pretty much the same way. Okay. So mutual inductance is this. Hope this is clear to you.